Good afternoon, students. So, today we will start our first class on low power VLSI design. Okay. So, this class will be mainly introductory discussion. So, we will just discuss the overall syllabus and which books and just the basic introduction to VLSI design. So, as you have gone through the few courses from last semester onwards, so you have the basic understanding of what is VLSI. So, I hope most of this discussion, today's discussion, it will be common to you. So, we will be discussing little bit about what is VLSI, what are the subject, what are the different kind of VLSI designs, what are the challenges. Okay. So, these are little bit overview we will be discussing, and for this low power VLSI design, these are the books that we will be mainly following. Okay. I have given you the MS Team link, you can join there, you will get the soft copy of the book there. Okay. So, that will not be a problem. So, mainly we will be following this low power VLSI circuits and system by Dr. Ajit Pal, and also for few circuits related discussions we will be following this digital integrated circuits. Okay. And these are other two essential circuits. So, if we follow some other book, I will discuss you, I will intimate you about the book. So, roughly you can say that for this moment these two will be our main book. So, in low power we will be discussing about what are the different low power requirements, and in this book we will be following what are the requirement of digital ICs, what are the design requirement for gates, okay, for delay, noise margin, power dissipations, both for combinational as well as sequential circuit. So, we will be differentiating between what is combinational circuit, what are different type of logic design styles. Okay. How many logic design styles you are familiar with? Static and dynamic. So, this is a CMOS design, right. Okay. So, CMOS you have static design you are familiar with, and as well as dynamic CMOS design, right. Okay. So, there are other type of design logic also, logic design style like the pass transistor design logic, complementary CPL. So, we will be discussing about those and which one is more efficient about from power low power perspective. So, that we will check. Okay. So, this is about me, this is I am Dr. Santanu Sarkar, as me you all have know. I done my BTech BE from Jadavpur University and MS and PhD from the IIT Kharagpur ECE department, E and ECE department. I did my postdoc from the NUS Singapore, and I am associated with this institute in the ECE department from June 2014 onwards. Okay. You know my mail ID, I have already mailed you. About the organization, we will be having the structure of 20 plus 30 plus 50, right, you all know that. So, 20 will be average of your class test or assignment, and then 30 will be mid sem, 50 will be end sem. Okay. So, the same books are written here in different order, but that is the book that we will follow. This is roughly our syllabus. So, if I do not go through this and I just discussed as a whole. So, first is introduction to low power. So, in this first chapter you will be learning about why low power, why suddenly low power is important, why in modern days it is becoming important. In say 10 to 20 years back it was not that of importance. Then, so why, what are the challenges, why this suddenly becomes so relevant, what are the different terminologies, how we could save the power. So, all of this will be on a broadly will be or superficially will be described in this chapter. Next, we will attack the problem from all design style, starting from device physics, technology level. So, in each level of abstraction we will try to reduce the power. Okay. your first abstraction is your physical design, right. So, what is your technology, how the technology is offering you different options to save power. Okay. So, from fabrication point of view, from the technology point of view, what are the things that we can do or the science can help, so that I can achieve low power. So, we will go through some device model, device structure, we will try to see that which device structure is suitable for low power, what are the different equations, what are the different way that power is getting dissipated, what are the different effects, non-ideal effects. Okay. Then technology wise, which fabrication style, which new technologies is offering more options to save power, that we will know. So, these two are, so first one is your introduction, just overall description. Next is device point of view. Okay. What are the different layout structure, what are the different device structure, what are the different short channel effects. So, all of these will be covered in these two chapters. So, this is mostly your geometry related, structure related, structure and device physics related. Next is we will be coming to supply voltage. Okay. So, if we roughly say, can you tell me dynamic power equation, P dynamic of CMOS circuit, roughly any equation? Half CV square F, right. So, roughly this is your equation, right. What is this C? C is your total load capacitance. Load means whatever you are seeing that you are driving, that could be next stage logic, right, or wire capacitance or whatever, or its self capacitance. So, C is nothing but C load. Okay. Bigger the load, bigger the power. Now, what is more dominant here, you see? VDD square, right. So, if you can scale down VDD, suppose you are using 180 nanometer CMOS technology and you are using 1.8 volt. So, if you instead of 1.8 volt, if you use 1.2 volt, you can scale down the power. Maybe our speed and specification will be hampered, that we will talk about it later, but from the equation we can understand, right. So, if we want to scale the power, so what we should scale? First is load cap, it should be less load cap, VDD we can scale down, then power will be also scaled down, and third is frequency of operation. If you want more frequency, suppose you want to run at 2 gigahertz, so you will have to burn more power. Now, if your requirement is not that fast, you can scale down the clock up to say 500 megahertz, and you can still do the job with your satisfaction of requirement, then you can save power, right. So, these are trade off, right. So, you may have heard those terminologies, trade off, design specifications. So, these all you already know, right. So, broadly you see that VDD is having square terms. So, if we can scale down the supply voltage, we can scale down the power dissipation. So, this is one important aspect, because it is having square terms. So, now scaling the supply voltage, what are the different ways, what are the different terminologies, techniques, and what are the drawbacks? There has to be some drawback, right, nothing is free, right. So, if we scaling down something else, somewhere the effect will be, right. So, we always have this trade off in this VLSI design, be it a analog design or be it a digital design. You will be always seeing that if I want to gain advantage is one aspect, other advantage will be compromised, right. So, we will discuss about this later in details. So, this is one important aspect, how the scaling can help in achieving low power and what are the corresponding challenges. Next is, so you see how we are progressing. First we will start with device technology, then we come to supply voltage. Now we are coming back to circuit design, how we can modify the circuit so that we can save power. Okay. So, in this case different type of logic will come, which logic is more power efficient, what modification we should do, okay, how we can design so that effective capacitance will be less. So, all of this will come in this. This is basically circuit modification for low power design. Okay. This was device, structure, fabrication, this is process, this is VDD, this is VDD, this is device and structure and fabrication. So, this is your circuit level. In circuit level means if you are talking about digital, this is RTL coding, and if you are talking about say transistor level, then it is transistor level design. Next is, this is combinational, this is for sequential, but aspect is same. Okay. This is also circuit level, or you can say block level. So, after that we will be coming back to effective capacitance, C effective. Okay. How we can, here in the equation C is one important aspect. So, if you can reduce the effective capacitance, then we can reduce down the capacitance, right. So, there is another term is there, that is called alpha. Okay. Here actually this half will come as alpha. Okay. This alpha is nothing but a switching activity, right. For example, suppose this is your clock, okay, and at say each clock you are flipping from 0 to 1 and 1 to 0, and in another case you are flipping after a very long time, right. So, this is your F, this is your clock, and between this signal, signal A and signal B, which one is switching more frequently? Switching A, right, A is switching more frequently. So, it will burn more power, right. So, if you are talking about the dynamic power, the more frequent the switching will happen, you will be burning more power. So, this is known as the alpha into this CL, they are termed as the C effective. So, this alpha is the probability of your switching, okay. How fast you are switching. If you are switching more fast, you will be burning more power. So, we club this with the capacitance and we term this as a effective capacitance. So, this capacitance is actually your effective capacitance. Okay. So, we have now two aspects. One aspect is that we can reduce down our capacitance by some way. For example, you may have heard about parallel processing, parallel or dividing by half, okay, or pipelining, where suppose you have a bigger combinational block, you break it into two chunks. Okay. So, one chunk at a time will be having less number of capacitance. So, these are different type of design styles that we will discuss in details later, but I am just giving you an overall idea. So, you just have an overall idea that how the things will be. Now, so one is physically you are reducing the capacitance, okay. You are improving your technology so that your wear capacitance is reduced down, right. When you are moving from bigger technology to lower technology, what is happening? Our size is getting reduced, right. So, if size is getting reduced and metal levels are improved, then what will happen? Your area is reducing down, right. If you compare say 180 and say 40 nanometer. So, we are scaling down, right. So, as we are scaling down, our capacitive load is also scaling down, right. The thickness of the wear say 10 years back and thickness of the wear now also scale down, right. So, effective capacitance size wise it is reduced, right. Now, another thing is your switching activity, that we can reduce by using several kind of algorithm, right. For example, you may have heard about gray coding, right, one hot coding. So, certain coding your transition are less. If you can recall the K-map, K-map follows the gray coding, right. So, consecutive bit change is only one bit is changed, right. We follow the K-map in that scenario. So, there are several algorithms where we can reduce down our switching activity. Okay. So, compared to binary logic, maybe gray logic, gray code logic we will be having can save some power, that we will see later. Okay. So, this how we can reduce the power by reducing the effective capacitance, this will be one chapter. So, circuit level, effective capacitance level, VDD level, and then another is this is architectural level. Okay. This is you can say that block level. Okay. Schematic level we already discussed, this is schematic level or circuit level, and now this is system level or block level, and top we are going to topmost level. So, on the architectural level what we can do so that we can save power. Okay. So, several techniques are there like the pipelining, clock gating, power gating. Have you heard this term? Any of this? Okay. So, few terminologies are there, few techniques are there which can be helpful in saving the power. Okay. So, we will be seeing this in details and some design examples, for example, how to design adder, shifter. So, these are common, maybe few in other syllabus you have partially covered this. So, this is just an example how we can implement this low power design technique into design of several sub block design. For example, memory, we will be covering memory design, okay, SRAM and DRAM design, and what are the different low power techniques as an example of implementing this low power technique into some design. Okay. So, this is grossly our syllabus. So, I hope the flow you have understood. So, what is the flow? Flow is that first we will see what is the power equation, then how we can target this, and what are the different abstraction level we can attack the problem. For example, starting from device, right, fabrication, technology, this is one aspect, then is design, circuit, transistor level diagram or logic, right. Next is this will include both combinational and sequential. Third is VDD scaling, capacitance scaling, okay. And next is system level or architecture level. Okay. So, this will be our flow, we will be following this pattern. Okay. So, we will start basically in today's class also we are at the introduction, next we will enter the device physics, next we will go to circuit and sequential, combinational both, then we will go to system. Okay. All right. So, this course objective and course outcome, that is this is you already know or this is very common. So, we will not discuss this. So, let us have some general terminologies that you are already familiar with. So, VLSI stands for very large scale, and basically we have surpassed the terminology, but still this terminology is quite popular. So, we are sticking with that terminology. So, presently we are actually at UVLSI or VVLSI, but still this VLSI we generally follow. So, if you see this terminologies, so SSI or small scale integration is few tens of transistor in an IC. Okay. Medium scale integration is few hundreds of transistors, large scale integration is few thousands of transistor in an IC, and very large scale is millions of transistor. Okay. This is hundreds of thousands or millions of transistor. Now, basically we are in billions of transistor, but still we prefer this terminology as this became very popular. Okay. Right. So, this VLSI, the development of this VLSI and this integrated circuit fabrication technology, that has changed the history, right. So, starting from the vacuum tube diode and these discrete components. So, these are few important eras of development, right. When the first time the vacuum tube diode was discovered, then we had integrated circuit, discovery of integrated circuit, and we used to have discrete component, right. All the discrete component, they were combined and made on a board, but this took bigger area. Now, later it was possible to fabricate all the passives as well the active component on a single IC, and that was when the actually this development started, right. You know the Moore's law. So, what is it? Transistor count will get doubled, right, roughly 1.5 year your density will be shrink, and so that on the same area you can use double the number of transistor. So, actually Gordon Moore, he predicted this, and that becomes so, even now it is getting saturated, but for a long time it was so accurate, and so it becomes like a law and we use this. So, he was a co-founder of Intel and he indicated first time that number of transistor in a microprocessor chip will increase at a rate of roughly 2 times per year. So, you can follow that how it was roughly so much accurate, and these are different processor and how this technology is shrinking and the number of transistor and as well as the power is going up. So, here you can see that it is power. So, you can understand with the shrinking of technology what is happening, that we can stack more number of transistor, right, as well as the capacitance, effective capacitance is reducing down, we can go up in frequency. Okay. And as we can go up in frequency, power will be also increased. Okay. So, that is why suddenly we started thinking about low power. Okay. So, why suddenly we started thinking about low power and why this low power design suddenly becomes so much important. So, we will discuss this about just after a brief time. So, these are few important inventions that change the lifestyle of human, and this VLSI, this is very closely related to our daily lives. Okay. Any major invention, any for just like any major invention in science, this invention also very closely related to our day to days activities, our use of different gadgets, right, different equipments, and this can change the history of mankind. For example, starting from invention of transistor or radio, then television, and now the era of smartphone, right. You all have a smartphone which is capable of like a comparable like a PC, right. So, these are few inventions that actually changed the mankind. One was the invention of the transistor, that is William Shockley, John Bardeen and Walter H. Brattain of Bell Laboratory. They invented on 23rd December of 1947 and they were awarded Nobel Prize later. Next is first patent for MOSFET by Julius Lilienfeld in 1929. Okay. So, the idea came first, but that time it was difficult to fabricate. Okay. That time technology was not that solid to implement that idea. So, BJT came first. So, first IC was invented by Jack Kilby of Texas Instrument. He was also awarded Nobel Prize. Okay. And later Robert Noyce of Fairchild. So, these are some big people from big companies. He also helped in improving it, and first microprocessor by Tedov of Intel, first microprocessor 4004 in 1971, approximately 2300 transistor were there. So, these are few milestones, important milestones that happened and that changed the face of the semiconductor industry. This is how the fabrication is done step by step. So, I hope you all are familiar with this, right. So, what is, suppose you have a NMOS technology and you have a, from NMOS you are coming to CMOS technology. So, what is the difference? Previously you had a suppose NMOS technology and now you have a CMOS technology. So, meaning is in NMOS technology you could only go with NMOS only, there was no option to fabricate PMOS, but in CMOS you can have both NMOS and PMOS, you can fabricate on the same wafer, that is the difference, right. So, for NMOS what is your substrate? P substrate, right. On top of P you have source and drain, right. What is source and drain? Which type of material? N type material, and in between them what is there? Channel, that channel is also P type. So, this P is global, right. P is actually your wafer. Now, on top of this wafer, so this is your wafer P, on top of this P you will be doping a region which will be N, getting my point. Then on this N you need a contact connection, right. This will be make a source, this will be make a drain. So, you need some metal deposition, right. This metal will behave like a ohmic contact, right. You need some connection, na. This is my silicon. Now, when you are making an IC you need some pin also, right, for the physical connections, right. You need to give some connections, na, source, drain, gate, when you draw a circuit. So, this is your silicon, first level is P substrate, on top of this you will be making a window of N, right, another window of N. So, one becomes source, another become drain, right. So, on top of it then what you will do? You will grow a oxide. How you can do that? You can may at a certain temperature or high temperature you can pass a oxygen, right. Then a oxide layer will be grown throughout the wafer, then where you do not need it you can etch it up by using several kind of chemical etching or physical etching, or but this is grossly the technique, right. So, when the oxide is grown, next step is polysilicon, right, metal oxide semiconductor. So, polysilicon will behave like a metal, okay. Polycrystalline silicon, which is a amorphic design, amorphic crystal structure which has a higher conductivity, which behaves like a metal connections and which is compatible to grow on above this SiO2. Okay. So, this becomes your NMOS. Now, for PMOS what should be your substrate? PMOS your substrate should be N. Now, you have a global wafer of P, that is the beauty of CMOS, your wafer is P, you have only one type of wafer, that is P substrate. So, this P is globally available, okay. Say you have a wafer. So, this is full of P type. Now, suppose this region you want to make a, this region is for NMOS, this region you want to make for PMOS. So, this region what you will do? You will make a well and this well should be of N type. So, as if this become a island, okay. So, suppose this full is my P substrate. So, this is capable of building up NMOS. Now, suppose this portion I have reserved for PMOS. So, what I will do? I will make a, I will dope this portion with N type. full portion, and say several PMOS I will be designing. Clear? That is one option. Another option is I will make a separate well for a single PMOS, separate well for a single PMOS, separate well for a single, that is also possible, that freedom I have. So, we will be discussing this later about details. Okay. So, this is roughly your, so this is what B stands for bulk or body. Okay. So, this connection, this P substrate, you need a physical connections, right. So, this is for your substrate connections, that is the fourth terminal. We generally have a 3 terminal, but actually it is a 4th terminal, this is the bulk or body. So, similarly for NMOS also we will be having a bulk or body, right. So, can you tell me for NMOS what should be this bulk connected? Ground. Why? Whatever you said is right, that it should be connected to ground, but why? PN junction reverse bias, otherwise what will happen? Leakage current will flow, that will flow to where? To ground line. So, this is a wastage and it will result in power loss. So, there is a, if you follow this, this is a PN junction diode. This P substrate and N source or N drain, they can make a PN junction diode. So that now if any current flows through this will directly go to the ground. This current is of my interest, right. The channel current is of interest. The current wasting to the ground line is, it is not my intention, right. So, I should stop this current. So, if source is grounded and bulk is also grounded, so as if they are virtually short. So, this PN junction there will be no reverse saturation current, reverse or leakage current. So, that is the idea behind this, doing this, right. So, for PMOS this bulk should be connected to, opposite thing will happen, right. So, it should be connected to the highest possible voltage, because now you see it is, this is cathode, right. So, it should be connected to the highest possible voltage. So, in case of NMOS bulk should be connected to ground, in case of PMOS bulk should be connected to VDD, this is by default, right. Now, you see in NMOS this P substrate is global, P substrate is common to all. So, all the substrate are actually sorted. So, in NMOS you will be seeing that you have no options, you can only connect to the substrate, should be always connected to the ground, because this is a global, this P substrate is common for all the NMOSs. So, one NMOS is at voltage V1, another NMOS substrate is at ground, that not possible. Your tool will give a warning, right. But for PMOS you can have a global NOL or you can have a separate NOL. So, in PMOS you can either connect this to VDD or you can sort it to source, that option is there, right. For example, can you tell me which gate it is? Okay. In this case you see this one, this substrate you can sort it with source because it is VDD, no problem. Now, you have two options, this bulk, one is you sort it with VDD, or if you use this like two of the PMOS in globally same well, that options you can do, or you can have separate well for this M1 and M2, right. So, if you have separate well, you can sort this bulk to its source, that is also possible, getting my point. So, you think about it, we will discuss this later. So, in PMOS although not suggested, generally by default you should all the bulk PMOS should be VDD, in NMOS all the bulk should be ground. It is rule and you should follow this, but for PMOS you can also, for this kind of structure, instead of VDD you can also sort it with source, that is okay, but you should not do this, but it is okay. Okay. It has a certain advantage and disadvantage, we will read about this later. Okay. So, you just I am just giving you, throwing you some different techniques, but which is advisable and not, or which is preferable or not, that we will study in details later. Okay. Okay. So, that is one aspect. Next is, have you heard this term latch-up? Okay. Can you tell me what is latch-up, or is it good or is it bad? Okay. I am just these are, I am just giving you some brief just introduction. So, do not worry about at this moment. So, latch-up was actually a problem. Okay. So, for earlier CMOS technology it was a challenge. Sometime few ICs were destroyed because of this. So, what was the thing actually? If you see just like that we draw some diode structure. No? So, this diode structure, they are not real diode, they are called parasitic diode, because physically no structure is there, but the junctions are making, can make like this kind of circuit component, right. So, these are not really, parasites are like some small elements, right. So, this can form. Okay. These are not real structure, but equivalent structure, you can say equivalent structure. For example, if I have a connector, ideally it should have a 0 resistance, but maybe small resistance are there, milliohm, right. So, this resistance we will be saying that it is a parasitic resistance, which is unwanted. Okay. So, this kind of structure NMOS, NOL, POL, and by combining them we can have a NP, N, PN, PN like of structure, clear, because we have some PMOS, we have some POL and NOL, right. So, we can have a this kind of structure, okay. And if it is turned on, so what may happen, large current can flow from VDD to ground. Suppose this circuit is on by somehow. So, this circuit is not really existing there, but because of the junctions, connections, these parasitic connections are formed, and if not properly designed or addressed, what may happen, this PNP and NPN, you see this is a PNP transistor, right, and this is one NPN transistor. So, if this VB, its VB gets, where it gets turned on, roughly 0.5 to 0.7 volt. So, if this is on, suppose this VB voltage is on, what will happen, this BJT will turn on, right. So, how it could turn on, suppose some current is flowing through this. So, there will be some passive resistance, I call some connections, ideally it is a connections. So, 0 resistance, but in reality there will be some resistance offered by the connections. So, some resistance will be there. So, if some current is flowing and some resistance is there, so some IR drop will be generated. So, if this IR drop is bigger and if it gets greater than this VBE, what will happen? This will turn on, right. If this is turned on, what will happen? This collector current will be also keep on increasing. If this is keep on increasing, this will be having some drop. Suppose there is no current flowing. So, this is VDD, this terminal is also VDD, no current flowing, 0 current, same voltage. So, this VB is virtually 0. Now, suppose some current start flowing. So, there is some drop and now it will be started to growing a VBE on. So, what is happening, first one current flowing. So, one gets on, this will in turn will turn this on. So, this will become a positive feedback, getting my point. Say you told na this there will be some reverse bias current, right, leakage current. So, due to that leakage current some IR drop will be there. That IR drop if it is growing and suppose it is greater than your VB on, this will turn on one NPN transistor, this NPN transistor will in return turn on this PNP transistor, and this structure will is like a one is turning on the other more strongly. So, it is like a positive feedback. So, it will keep on growing, and what will happen at the end? So large current will flow that the structure will break because of higher melting or maybe temperature or destruction. Okay. So, that was a problem in the CMOS circuit, earlier CMOS at the beginning. Now, technology is quite matured and generally we do not see this problem. Okay. So, there are certain ways to, so this is called thyristor circuit, okay, in PNP structure, but the concept is like that. Okay. And how this formed, you can see that there are several N and P structure. So, by connecting them we can make a this kind of structure. Okay. So, you do not need to worry, just I am just giving you the idea, later maybe we will be covering this in details. Okay. So, whatever I am discussing this, maybe I will be discussing this later also. So, you do not need to worry. Okay. Next is technology, some hints that how the technology could help us in designing low power circuit. So, one but this is how to we can reduce the latch up, this is called guard ring, guard boundary. So, I am just giving you just one small hints that how we can do that. See this circuit, this R, you see these two R are actually generating this VB drop, right. If you can reduce down this R, so what will happen? IR drop will also reduce down, and if IR drop is reducing down, it will be difficult to generate the VB on, right. Base voltage is first generated na. If base voltage is higher than the cutoff of the that diode, then only it will get turned on, right. Three modes of operation, right. One is cutoff, one is linear, one is saturation. So, if we can somehow reduce this resistance, so what will happen? My IR drop will be reduced. So, it will be difficult to turn on the BJT. So, what is this R? You see this R is nothing but bulk connection. You see this was bulk, this is bulk. So, this is bulk resistance, this is bulk resistance, this is bulk resistance. So, what is the meaning? Meaning is that I have a MOS na, this is my source and this is my bulk connection, right. I have a MOSFET, this is my source, this is my gate say. So, these three are my connections, gate, source, drain. Another fourth terminal is there, when you will be doing the physical design, fourth terminal should be there. So, fourth terminal is generally we use one P tap and one N tap. We use some P tap material, we place it here which acts like a connection for the P well. Okay. You see that this is a P substrate na. So, this is a P plus doping, and on this P plus doping some metal connection is there, that is it. So, what is a P tap? P tap is nothing but a P plus, and on this P plus some metal deposition. So, if you have a marks like that, so this is P plus, and on top of this P plus you have a say metal 1. So, that will act as a short for the P substrate, clear. So, this is a mask just to ensure that P substrate is on this, you have a ohmic contact. So, that P is connected to that metal. If you now carry a metal 1, it will be a connection where, that is it. Okay. So, these are some terminologies, when you will be doing layout in lab you will understand. So, do not worry, okay, about the terminologies, these are some techniques. that you will be learning in laboratories. Okay. So, my objective is to reduce down the R, which are for the connection of the bulk connections. So, if you just think that way, if I have several resistance in parallel, what will be the effective resistance? Go up or go down? Go down. So, instead of a single contact, if I can have a multiple contact, so the contact resistance will go down. So, instead of a single p-tap contact, if I can use multiple contact, my connections will be more stronger. Suppose you have a, this is your metal and you want to sort it with metal 2, you will be using some via, some sorting material, that is termed as via, so that this is sort. Now, if you are using only single element, there is a chance that it will be misplaced, it may happen, right. You are in the nanometer. So, if it is misplaced, this connection will be weak, only this portion is making this sort. But if you have a multiple contact, then your connection is strong. Drawback? Obviously, there are drawback, you are getting more area for the sorting. So, there will be always trade off, okay. More contact, more solid connections, but well, area is getting more. So, if I can have multiple contact or p-tap for the that substrate connections, then my resistance will go down. And even they used to say that all the NMOS, suppose you have a NMOS, all the NMOS are here, you better make a ring and connect this ring to the ground line, then it will be even more strong. Okay. So, these are several techniques, ways to reduce down the latch-up. So, we will discuss this is later. Okay. Another technology wise, how we can reduce down the power is SOI technology. Have you heard this term SOI? What is that full form? Okay. Silicon on insulator or okay. So, that previously it was your substrate, your MOS was grown on substrate. Now, your this NMOS and NOL and POL, they were grown on p type substrate. Now, in this they will be grown on some insulator, that means SiO2. Okay. So, this is your insulator SiO2. On top of this you have a N plus or P plus, whatever material you want to make it. So, now what is happening? Previously you had a leakage current problem. Now, that is, as this is a insulator, that leakage current problem is solved. In previous case you have a parasitic capacitance problem, right, because this substrate can behave like a one metal of a capacitor and can build up your parasitic capacitance. Parasitic capacitance will eat some of your power, right. The moment this capacitance is charged or discharged, one C was there na, in dynamic power equations. Now, in this you are growing it on insulator. So, that bulk capacitance problem will be gone. So, it will be little bit faster because of you do not have any this capacitance discharge problem, that problem is not there. So, this had certain advantage, but at there must be some cost, nothing is free. What is the cost? Technology is costly. When we go to buy something, what we see first? We are budget, right, whatever is cheaper, we always try to compromise. We wish to get a better spec, better specifications, but then we look at our pocket and we trade off, right. So, same thing, generally we go for cheap fabrication. So, we choose CMOS. This SOI for common people or the academic people, we always have a problem of budget. So, this is good, but costing is more, okay, because you can understand that some separate fabrication technologies should be there, right. So, you may have, you need more. So, as well as, so this is having some advantage, but at the cost of more money. Okay. So, here in this case, because of the isolation, latch-up possibility is also improved. This you already know that what is a planar IC, what is wafer, what is the dye photo, right. So, this is all a single integrated circuit. This is a full wafer having several die 1, die 2, die 3, right. They actually they get cut off, okay, like the sawing. Okay. So, each one is will be making one IC, they will be packaged. So, if you open up the package, you will be seeing the actual silicon die at the center. Okay. So, on this, so actually this is your some planar IC. So, these are the pin connections, these are pin connections, and to make this pin connection possible, these are all some input output pad, these are called the IO pad. Okay. So, some IO pad will be for VDD, some IO pad will be for ground, some IO pad will be for input and output, and the pin is actually glued to that. So, from this pin, one very thin wire, maybe gold wire, will be taken to that pad, and physically it will be hammered, or will be glued with some special kind of adhesive or both to make a real connections. You see how many steps are involved with this technology, how different job aspects are generated. You need device people, you need fabrication support team, you need packaging team, to design the IC you need team. Okay. So, this is a big industry. Okay. So, we will end up today, we will end here, and in next class we will continue from this.